Discovery of the solar wind. Years ago, space was considered a vacuum, except for a curious clue, the tail of a comet.
All right, so the tail of a comet points away from the sun.
Regardless of the direction it traveled, its tail always pointed away from the sun.
So why does the tail of a comet always point away from the sun? Wondered Newton 350 years ago. He had a theory. He said, oh, the tail must be composed of particles. And he knew that the tail was composed of particles somehow.
A mystery on.
Yes, the tail of a comet is composed of dust as well as ice particles. Okay, we know that for a fact today. He must have guessed that back then. All right. So the question is, what's coming out of the sun and pushing away the dust and the ice particles?
Explain.
Obviously, what's coming out of the sun is light. We got heat, but also light is coming out of it. So he thought that the light must be composed of particles. So the particles of light colliding with the particles of the tail, dust as well as the ice particles, are simply pushing the tail away from the sun. That's the way he was looking at it.
Until the discovery of the solar wind. 30 years ago, space was considered a vacuum, except for a curious clue.
All right, so the tail of a comet is pointing away from the sun. Everything is being pulled in this direction by gravity, but something is pushing the tail away. So that something is light. Light particles just colliding with the particles making up the tail is just pushing the tail away from the sun. All right, so that's the way he was thinking. He thought that the light was composed of waves. This guy on the right, his name is Christian Huygens. This guy is a Dutch mathematician and a physicist who disagreed with Newton. He thought that the light was composed of waves. Light was composed of waves because waves interfere. Number one, waves will carry energy, but they will interfere. They can interfere constructively, which means that the light is going to become brighter, or they can interfere destructively, which means that there's going to be a lack of light, like the shadows. So as far as he was concerned, the light was composed of waves. So the decisive experiment was carried out in 1801 or 1803, depending upon what your source is, by this guy. His name is Thomas Young.
Here's just one of the reasons Young is so clever. He decides to shed a little light on light in 1803. Okay, watch this bit of magic. Here we have a candle, a lens, a card with a pinhole in it, and one with two slits. Okay, shine the light from the candle through the lens so you get a nice focused beam. Then carefully place your cards so that the light goes first through the pinhole, then the slits, and voila! Young realizes the light going through the slits and mingling must be coming in light waves, because this interference pattern could only be made by waves. Question is, what do light waves travel in? They decide to call the mystery stuff ether, and the hunt for it shakes up the brains of most of the 19th century's complement of serious propeller heads. Now, the biggest propeller in Germany at the time is a Harumph type, name of Helmholtz, prof at the University of Berlin, and he puts one of his whiz kids, Hertz, onto the case. Here is a very oversimple view, of what Hertz does. Say this water is that mystery ether stuff, right? Hertz is into electricity at the time and wonders if it travels through ether in waves like light. And he finds out it does. An electric spark sends out electric waves moving like light waves, or waves in the sea.
All right.
Here's just so that the light goes first
So let's focus on the Young's double slit
through
experiment.
the pinhole, then the slits,
So the same light is going to go through two slits.
and voila!
And then here's the screen.
Young realizes the light going
And then you end up seeing a fringe pattern on the
through
screen.
the slits.
You end up getting this fringe pattern. So what does the fringe pattern indicate or prove regarding the nature of light? Here's what it does, guys. You got the dark fringes and you got the bright fringes, right? So what's causing the dark fringes? Lack of light. How does the light become lacking immediately? Well, that means destructive interference. Bright fringes towards the middle, they will get brighter. So what's causing that to happen? It's the constructive interference. So the constructive interference is going to make light brighter, and destructive interference will simply cancel light. So what does that tell you about the nature of light? It tells you that the nature of light is, it's a wave. All right, so constructive interference is going to give you bright fringes. Destructive interference is going to give you dark fringes. And then the solution is that light is a wave. So which means that Newton was wrong. So Newton proposed that the light is a particle based upon the tail of a comet, 1680. 10 years earlier, Huygens proposed that the light is a wave based upon the superposition of waves, which means that the waves will interfere either constructively or destructively. 1803, Young's double slit experiment conclusively proves that the light is a wave. All right, guys, pick out the best answer and jump in whenever you're ready. Which the best answer is C, right? All right. So interference experiments proves that the nature of light is a wave nature. All right, those guys who picked that, give yourselves 2 points for it. All right, so whenever you're ready.
C.
All right, Flora, give yourself 5 points for that one. Interference is the right answer, right? So the interference phenomena, constructively or destructively, will prove that the light is a wave. All right, so here's the history of it. Huygens, 1670s, came up with the wave theory of light. Newton said that light is a particle based on the comet, the tail of a comet. 1881, no, it's 1803, Young, through a double slit experiment, proves that the light is a wave. 1865, Maxwell publishes his theory of electromagnetic waves, according to which light is a wave because it's moving. All electromagnetic waves are traveling at the light speed. And he proposes a medium called ether within which the light can travel at the light speed. In 1887, Michelson-Morley experiment proves that there's no ether and the light moves at the light speed relative to everyone. That later became Einstein's theory of special relativity. All right, so the conclusion is light is composed of waves.
And here we are.
How about us? Are we composed of particles or waves? We're composed of particles, right? We're composed of atoms. Atoms turn into molecules. Molecules turn into cells. You become you, I become me, and we have this discussion. So these particles, called atoms and molecules, make up reality.
The granddaddy of all quantum weirdness, the infamous double slit.
So if we were to do the infamous double slit experiment using particles like atoms, electrons, and molecules.
Experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we
So they would act like particles, right? Because they're particles.
randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit.
All right, guys, particles will always behave like particles, so you're not going to get an interference pattern.
Now, if we add a second slit, we would expect to see a second band duplicated to the right.
Which means particles will still act like particles.
Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So when we throw things, that is matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now.
All right, so what do you think is going to happen when you do the experiment using particles? Are we going to get an interference pattern, or are we going to get just bands, two bands?
Let's go.
Will we get an interference pattern?
Particles would not give you interference pattern, would they? No, so you should get bands. Give yourself 5 points for saying the wrong thing.
An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern.
All right, guys, excuse my French, but what the fuck has just happened? When you're using particles, you shouldn't be getting a fringe pattern. You should be getting just bands, two bands. Instead, you end up getting a fringe pattern.
We find.
What the fuck just happened? We weren't expecting that. This is called an animation, obviously, for those of you guys who don't know, because you guys live in mycelia. This animation actually represents a reality that took place in the 1920s. My reaction is exactly the same fucking reaction that the physicists had. What the fuck just happened? Because we're using particles, we should not be getting an interference pattern. Particles should not be giving you an interference pattern, period. There's no such thing.
Electrons.
Electrons shouldn't be giving you an interference pattern.
Tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave?
They shouldn't.
It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they can interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits and it goes through neither. And it goes through just one and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many.
Oh, so if you're watching them, they act like particles.
The very act of measuring or observing which slit it went through meant it only went through one.
If electrons know that they're being watched, they act like particles.
Not both.
And if you don't care which slit they go through,
Electron
they act like waves.
decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange netherworld of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
Bunch of questions. Reality is made up of particles, guys. You're made up of particles. The universe is made of particles. We're all made up of atoms, molecules turning into cells. You become you, I become you. We have this discussion. So, reality is made up of particles, except these particles act like particles when they're being observed. And when no one is observing them, they act like waves. The question is, waves of what? Waves of what? So light, is it composed of waves or particles? All of a sudden we got that question again. All right, so if you're not observing, electrons, atoms, molecules, all act like waves. If you're observing, they will act like particles. Sunglasses, what's the purpose of sunglasses, guys? Aside from making you look cool, why do we have sunglasses? What's the idea behind the sunglasses? The idea behind the sunglasses is to reduce glare. All right, so sunglasses, how do they reduce glare? Because they polarize light. So what's polarization? Polarization is related to the preferred axis of vibration. When somebody says something is polarized, which means that it's got a chosen axis of vibration. Notice that this thing is vibrating up and down. This is the vertical direction. This is known as a vertically polarized wave. Notice that this one is vibrating sideways. All right, this is a horizontal vibration. All right, so this is horizontally polarized. This is a horizontally polarized wave. This one is a vertically polarized wave. You can pick and choose the axis of vibration by using things called polarizers. So this is called a polarizer. Notice that you have a slit. Notice that the slit is vertical, so this is known as a vertical polarizer. Incoming wave is vertically polarized already, so it's going to go through. But notice that the horizontally polarized wave is not going to go through. It's not going to gain admission. All right, so we end up using polarizers. Regular light is not polarized. Electric field component of light is vibrating at random directions. So the oscillations are at random directions. You can actually take these oscillations at random directions and then send them through a polarizer and pick and choose the axis of polarization. All right, so this is unpolarized light on the right. On the left, you end up getting a polarized light, which means that it's got a chosen axis of vibration on the left. So how do you take something which is unpolarized and make it polarized? You have to use a polarizer. When you send it through a polarizer, only the components of light, which is along the direction, along the axis of polarizer, is going to get polarized. So the polarizer is going to pick and choose the vibration, the components of the vibration that it's interested in. All right, so it's a vertical polarizer, which means that the light going through is going to become vertically polarized. All right, so if you have two polarizers, get them 90 degrees to each other, notice that no light is going to be able to go through. Through the first one, the vertically polarized light is going to go through. The second polarizer is placed 90 degrees to the first one. The axis is rotated by 90 degrees, so which means that no light is going to be able to go through the next one. That's what it means. All right, why do we get glare? What causes glare is the horizontally polarized light. All right, what causes the horizontally polarized light is the light from reflective surfaces like wet surfaces, like water or ice or sun or metal surfaces. All right, so the reflected light at certain angles is going to be horizontally polarized. So how do you get rid of the horizontally polarized light, which happens to be a glare? You get rid of it by using sunglasses. Sunglasses are vertically polarized, so they will eliminate horizontal polarization. All right, whenever you're ready, just pick out the best answer.